Thank everybody for joining today. You have wandered upon the Sci-Cafe, or the Apalachicola National Estuarine Research Reserve. My name is Anita Grove, and we have a special speaker today, Guy Means, and he's going to talk to us about the Apalachicola River, its geology and geological history. As you know, it's one of the, it's the largest river in Florida in terms of flow. And I'm going to turn off my camera here in a minute, still waiting for a few people to join in. We will be recording the webinar, and I put the link to that in the chat. Also, if you have a question, feel free to come off mute at the end, or if you're shy, you can just type it in the questions box. I'll be monitoring that. And let's see, I have covered up my notes now. Hang on just a second. And we started this series a couple of years ago. We used to do it live, but we've gone to an online format after COVID, and it's worked for us, so we've kept doing this. But this is a chance for us to introduce residents and interested folks, scientists, to the different types of science that's going on in Apalachicola Bay, in and around. Today we welcome Guy Means. He is the state geologist, director of Florida Geological Survey, and he's long studied the Apalachicola River, and we're going to have him talk to us all about the unique features there. So, Guy, I'm going to let you take it away and turn off my camera. So, welcome.
Right. Thank you very much, Anita. I appreciate it. I'm happy to be here, and as you've already said, I've spent, well, actually my entire life here in North Florida. I was born and raised in Tallahassee, and for those of you that don't know, my father is a local ecologist and has spent much of his career studying some of the unique and endemic things from an ecological standpoint that occur in and along the Apalachicola River. But today I'm going to talk to you a little bit about the geology and the geologic history of the Apalachicola River. So as you've already heard, Florida at the Apalachicola River is Florida's largest river by volume of flow. The longest river in the state of Florida is the St. Johns River, so don't confuse those two. A number of really unique and interesting things about the river include it's the only river in the state where the headwaters reach all the way up into the southern Appalachians. And the Apalachicola River actually starts at the Georgia-Florida state line at Lake Seminole, where the Flint and the Chattahoochee rivers, as well as Spring Creek and Fish Pond drain, come together. And from the Jim Woodruff Dam, where the Apalachicola begins, the Apalachicola River flows all the way down to the Apalachicola Bay, some 106 miles, and it is unimpeded in its course to Apalachie Bay. So our story is going to start hundreds of millions of years ago. And before we get started on this, you know, talking about the geology of anywhere can, you know, it encompasses a lot of time typically. So we're going to skip through a whole bunch of time, but there are some key points that I'm going to try to make. And just remember, you know, any discussion of geology and geologic processes, particularly one as complicated as the geology in and along the Apalachicola River, could probably encompass, you know, multiple college courses. So I'm just going to attempt to touch on the high points. And at the end, if you guys have some questions on things that I didn't touch on, I'd be more than happy to try to try to address those. So just to give you a little bit of geologic history of the state of Florida before we narrow down into the Apalachicola area. Florida, it turns out, is interesting in a number of ways, and part of it is because of its geologic history. It turns out a little fragment of the current continent of Africa is part of what we call our basement rock. Basement rocks of Florida are related to rocks that we find on other continents. So how can that be? Well, for those of you that don't know, the underlying theory of geology that continues to develop as we gather more and more information is what we call plate tectonics. And plate tectonics helps us explain how the continents ultimately move around on the face of our planet. And periodically, it turns out, those continents can all come together and they form what we call a supercontinent. So the last time that happened was at the end of what we call the Paleozoic era, and that supercontinent was called Pangaea. And you can see sort of a representation of what Pangaea looked like about 200 million years ago. And you can see the outline of, here's the United States here, and here's Florida. So kind of keep an eye on Florida here, but you see where Africa is. So it turns out Pangaea, when it came together because two independent supercontinents, the continent to the south, which is called Gondwana, and the continent to the north, which was part of North America, or North America was part of, was called Laurasia. So when those two big continents collided, the supercontinent of Pangaea came together, and as is always the case with plate tectonics, plates always continue to move. So at some point, Pangaea began to what we call rift apart, so it broke apart. And that started about 200 million years ago at what we call the Triassic-Jurassic boundary. As geologic time progressed, the continents continued to separate, and what ultimately happened was, as I said earlier, a little piece of the continent down here that we now call Africa, which was actually part of a larger continent called Gondwana, left a little piece of land sutured to the North American continent, and that little piece of land ultimately became where we live today, which is our lovely state of Florida. So how do we know this? So as geologists typically do, we study rocks, and you've heard me use the term basement rocks a couple of times now. So our basement rocks are buried very deeply beneath the surface. And in northeast Florida, it turns out those basement rocks are about 4,000 feet beneath land surface. As you go further south, they're more deeply buried, and you don't encounter them until about 12,000 feet or more beneath land surface. But it turns out they are igneous and metamorphic rocks, and what's interesting about them is the similarities between these basement rocks we have in Florida and rocks of similar age that occur in Northwest Africa. So that is one line of evidence that helped us understand that what was going on here in our basement rocks is actually related to the formation of Pangaea and then its ultimate break apart. So what was going on around where Florida ultimately would be during the Mesozoic? Well, as continents rift apart or break apart, it turns out the land can fault and fracture, and it creates these basins. In fact, a good analog today is over in Eastern Africa. The big East Africa Rift Valley is a current, or is a modern area where we have rifting going on today. And if you ever have the opportunity to go over there, you see there's lots of volcanic activity going on, but there are lots of faults along which the land can sort of slide down into these features we call grabens. And along these faults, you actually have the injection of igneous material, typically what we call basalt. And throughout throughout the latter part of the Mesozoic era, as these faults continued to be active and these basins formed, all of the material from these higher regions could erode and then fill up these basins. And it turns out at some point, sea level became high enough and the rifting became significant enough such that seawater filled in that area. So we'll back up here. So here's this seawater that filled in. You can see Florida is completely underwater here. And that's when we start to see the deposition of carbonate material. So carbonate rocks in Florida anyway are limestone and dolostones. And the reason I'm highlighting this is because it turns out this low area here that we call the Tallahassee Graben, if you look real closely, it seems to correlate pretty well with where the current modern Apalachicola River dumps into Apalachee Bay. And this may have been the original low spot through which over geologic time allowed the Apalachicola River to actually exist and flow to where it does today. So during the Cenozoic era, which is about the last 65.5 million years, throughout the first part of it, most of Florida, if not all of Florida, was completely submerged. And as you know, as sea life lived and died, it would accumulate on the seafloor and eventually build up. And over geologic time, all of that carbonate material could become lithified, forming very thick deposits of limestone. During the what we call the Paleocene and the Eocene epochs, from about 65.5 million years to about 33.9 million years, that's what was going on where Florida is today. Thick sequences of carbonates were being deposited. And you see here in my graphic, this is an example of the oldest rocks that occur near the surface in Florida. These are Middle Eocene of the Avon Park Formation, about 45 million years old. And what's interesting about this is these are impressions of fossil seagrass. And that tells us that, you know, conditions that exist currently today out in Apalachee Bay, where we have seagrass growing in the modern environment, that environment of deposition has been around for at least 45 million years here in Florida. Another important thing that was going on at this time, a feature called the Georgia Channel System was occupied by a current called the Swanee Current. And that current was pretty important because it kept all of the material that was eroding off of the continent further to the north of us, where sea level was higher at the shoreline. All of that material that was being eroded and brought down into the marine environment was sort of shunted away from Florida. And that's important because that allowed these carbonate deposits to accumulate. Carbonate typically only occurs when you've got really clear seawater, and it can be fouled anytime you have the input of what we call siliciclastic sediments, so things like clays and silts and quartz sand. And I'll give you some graphics to help you understand this a little better. So this thing we call the Georgia Channel System actually it existed probably from the late Cretaceous all the way into the Miocene, and at various times it was active depending on where sea level was. And what effectively it was is it was a current that swept through this area, and it was much like the modern day loop current that now goes around South Florida, goes around the end of Florida, and then finally joins and becomes the Gulf Stream. And you know how important the Gulf Stream is today. It goes all the way up the northeast coast and actually all the way over into the North Atlantic. So when sea level is high enough, that current doesn't have to go all the way around here. It can actually, you know, cut across wherever the sea level is high enough for it. And again, anything to the north that was shedding sediment off of, you know, the southern Appalachians were eroding. All that sediment that ultimately made it by rivers down into the marine environment, this current then could take that material and it kept it away from Florida. And, you know, for those of you that know something about coral reefs, you know, coral reefs don't tolerate the input of things like clay and silt and sand, and they need, you know, really clean, clear water in order to thrive. So that's what was going on here in our part of the world for many millions of years, and that allowed the deposition and buildup of all of this carbonate. And this whole environment is what we would call a carbonate platform. And again, this graphic here is just simply to illustrate again. Here's this we call it collectively the Georgia Channel system, but at any given time, it was called various things as sea level was high enough for these currents to come through here. And you don't need to pay attention to the rest of the stuff. So you've heard me use the term the Florida platform. The Florida platform is actually this giant thing here, which is about twice the size of the currently emergent portion of the Florida Peninsula. So this, you know, this is a very shallow, and certainly those of you that like to go deep sea fishing understand this. How far offshore do you have to go before you get in water that's, you know, even 100 feet? You have to go quite a bit out into the Gulf here. So this area is what we collectively call the Florida platform. So this story is intimately tied to sea level. And hopefully everybody knows that sea level is never static. It changes constantly through geologic time, and it's obviously changing as we speak. But over the last 65.5 million years, this graphic represents where we believe sea levels were. So this dotted line here represents where modern day sea level is today. Any of this blue line above that means sea level was higher than it is today. And then of course, anything lower than that means sea level was lower. So you can see here, as we've already discussed, through the first portion of the Cenozoic here throughout the Paleocene and Eocene, sea levels were higher than they are today. A couple of times you got, you know, low enough where there might have been an isolated island that was exposed on the Florida platform, but for the most part, probably not. And it wasn't until this time right here in what we call the Oligocene Epoch, about 30 million years ago, when we had a precipitous sea level drop. And since that time, sea level has gone up and down, up and down, up and down, and you can see what that looks like with respect to present day sea level on this graph. So during the Oligocene, about 30 million years ago, Florida finally emerges from the ocean for the first time during the Cenozoic. And part of how we know that is that some of the first fossils of terrestrial mammals found in Florida are from this time period. So, you know, obviously you're not going to have terrestrial mammals swimming way out here if it's way underwater and then dying and falling onto the ocean floor. So we find them actually in sinkhole deposits down near Gainesville, is where some of these oldest terrestrial vertebrate fossils come from. So again, you can see here's part of the broader feature that we call the Georgia Channel system. At this time during the Oligocene, it's called the Gulf Trough, and here is this current that would have swept through here. We believe that, you know, as sea level was dropping, as Florida emerged, it probably emerged originally as a series of islands. And during this time, as sea level is dropping, this feature right here begins to fill in with sediment. And it turns out from the Miocene, from about 23 million years ago, right at the first part of the Miocene is when that feature starts to fill in enough, and then we get the deposition of sands and clays starting to spill out and cover parts of Central and all the way down ultimately into South Florida. And that's where our cover of silt and sand and clay ultimately came from. During the Miocene and Pliocene epochs between 23 and 2.6 million years ago, sea levels fluctuated as my graph earlier depicted. All of these siliciclastic and carbonate units accumulated across the platform, so we had new formations forming, and we'll talk a little more about these here in just a bit. And these formations that are highlighted here are actually exposed along the Apalachicola River. And then finally, during the Pleistocene epoch, which was between 2.6 million years ago to about 11,700 years ago, down in extreme South Florida, we had the deposition of limestone because it's still fairly far removed from the input of the siliciclastics that tend to foul carbonate deposition. But up here in North Florida, we had quite a bit of deposition of sand and sandy clay and clays. And during this time, during the Pleistocene, is really when sea level fluctuated greatly, and it fluctuated between 60 and 100 feet higher than it is today to as much as 350, maybe even 400 feet lower than it is today. So that's quite a bit of fluctuation. And this is a picture of one of my favorite places on the planet. This is Alum Bluff, just north of Bristol. If you haven't been there, I would recommend you visit. And then finally, the most recent geologic time period is what we call the Holocene. And that's from about 11,700 years ago and we are still in it today. And that's really when the modern delta and the barrier islands and the mouth of the Apalachicola took shape and started to look much like it does today. During the Holocene, sea level was rising rapidly, and it turns out the Apalachicola, the actual paleo channel of it, probably flowed further to the west. And we know this from seismic data that has been shot around here. We can actually see paleo channels that are cut down into some of the older strata that are buried out here offshore currently today. And as sea level rose rapidly, it would backfill into these old paleo channels, and then eventually the channel could shift. And about 6,000 years ago, they believe, the delta where it currently exists today started to build. And then finally, about 3,000 to 4,000 years ago, sea level stabilized where it is roughly today. And that's when we started to see the development of our modern barrier islands and spits, like St. Vincent Island and Little St. George. So all of the sand that we see down here, all of this material that makes up all of these barrier islands, all of that came down as the southern Appalachians eroded, and that's where all the sand on all of our beaches ultimately came from. So kind of just to recap what we've just discussed with respect to the paleogeography of Florida over the last 65.5 million years, at least give you a graphical representation of it. These detrital clastics, these are the siliciclastics I've been talking about. So this is where the paleo shoreline was, and this is where all of the rivers and whatnot were making their way down and bringing some of that eroded material into the marine environment. But during the Paleocene and Eocene, these marine currents that swept across here through the Georgia Channel system kept all of that material sort of shunted away from Florida. And as we go into the Eocene and down into the Oligocene, the same thing is going on here. And it wasn't really until the earliest part of the Miocene when that feature finally starts to fill in, because sea level has dropped sufficiently for this now to reach all the way down into this part of North Florida. And then you get into the later Miocene and Pleistocene, and that's when we see a real influx of these siliciclastics into what had been for millions and millions of years strictly a carbonate environment. So topography. I always like to say that Florida is topographically challenged, and I think we are. We can all agree to that. Florida has the lowest high point of any of our 50 states, but we still do have some topography. And this digital elevation model here is an interesting way to visualize some of this. So you see the Florida state line here. You see many of these features in Peninsula run parallel to the modern shoreline, and you can appreciate hopefully why that is. But when you get up in here into North Florida, this is where we've got some of the highest topographic relief, and particularly in and along the Apalachicola River. But what I'd like you to really pay attention to here is a very abrupt change in elevation that geologists call an escarpment. This is called the Pelham escarpment. And so what this reflects is that all of this material in here that was once presumably as high as this is now gone. Well, where did it go? Well, we believe that the probably the Paleo Chattahoochee, it flowed through here and it eroded down, and ultimately it eroded all the way down to the limestone bedrock which occurs in this area. For those of you that know this area, it's called the Doherty Karst Plain because limestone is either at or very near the surface. So as the Chattahoochee River eroded down into and finally got to the top of the limestone, a lot of that material subsided into karst features, but a lot of it was also removed and transported down river systems. Now, there, interestingly, if you look at the topography in this part of Florida, so here's Chattahoochee, here's the dam, here's Lake Seminole. It's been hypothesized that if you look at the elevation differences here, you can actually almost see an old paleo channel through here. So it's been hypothesized that all this material that got eroded away here was eroded by a paleo river system that came through here before the Apalachicola actually became a river. So what probably ultimately happened is you had a small stream that eroded back into here and ultimately was captured. And the Chattahoochee and the Flint were captured to become ultimately the Apalachicola River. And that probably happened sometime in the latest Pliocene, maybe early Pleistocene, maybe. But again, you know, that's a hypothesis. But it sure looks that way from the amount of material that has been removed in this area. So the topography also reveals something else interesting about this area. And for those of you that have ever been out to the Apalachicola bluffs and ravines, you've seen these. So there are ravines, but there are different kinds of ravines depending on where you are and depending on what the underlying geology is. Up north, up near Chattahoochee, if you look at the distribution of these gullies, you see it's kind of a dendritic pattern here. It looks kind of you know, like kind of like your lungs, if you will. But then you get down here to near Alum Bluff, and all of a sudden these things start to look a little different. It's because there's a huge pile of quartz sand sitting here, and you can actually, if you squint real good, all of these linear features you see in here, this is a paleo dune field. So there's a bunch of quartz sand sitting on top of a clayey unit called the Jackson Bluff Formation. And it turns out when you have those conditions, the type of ravines that can form in those are unique, and those are called steephead ravines, as opposed to these gully eroded ravines up here, which the sand layer is incredibly thin up here. It may not exist at all, and in fairly short order, there's limestone near the surface. So the superficial erosion is quite a bit different. So that's another neat and unique feature we see in and along the Apalachicola River. What's the superficial geology in this area tell us? Well, up here around Marianna, so this is Jackson County, the blues and these reddish colors, these are limestone units from the Eocene and the Oligocene, that time period from when Florida was completely submerged. And so these are super old limestones. And you can see right here a little bit up in the upper part of the Apalachicola River, there are probably Oligocene limestones in the bed of the river here, but certainly above the dam, you start to get these older limestone units. But as you go south, you get into these greens, which are Miocene in age, and then finally you get down here just near Estefanolga, and you get down here, and all of this stuff is pretty modern material. This is what we call Pleistocene to recent undifferentiated quartz sands. So this is the surficial geology. We'll talk a little bit about these geologic units. So what geologic units can you see exposed along the river? Well, since there's not a whole heck of a lot of topographic relief in Florida, we certainly don't have mountains and canyons. Some of the best places to see geologic units in Florida, at least from a natural standpoint, are along our river courses. And the Apalachicola is probably the best river in the state for looking at different geologic units. Each one of these red arrows here points to a geological formation that we can see exposed along the Apalachicola River. And you see the ages for these. The oldest one that we can see readily, then you don't have to dive down to the bottom of the river, is the Chattahoochee Formation. So what I want you to understand is that typically geologists, we talk about things from oldest to youngest, and we'll do that here. But what I want you to appreciate and understand is that the oldest units exposed along the Apalachicola River occur all the way up here in the north. And so as you go further south, those geologic units dip, and they dip to the south and to the east, such that you have younger units stacked up against them. So the oldest units in the Apalachicola Basin are all the way up here near, well, actually at the dam. And those are those early Miocene units, including the Chattahoochee Formation, which we'll talk about. So when you head south along the Apalachicola River, you'll know that the further south you get, the younger and younger the sediments and formations are, you see exposed along the river. There are some incredibly important places along the Apalachicola River where geologists have defined various geologic units. These are four really great exposures of various formations. We've already talked about Chattahoochee. Some of you hopefully have been to Rock Bluff before in Torrey State Park. And then of course the famous Alum Bluff there just north of Bristol. There's also a nice bluff at Bristol that we'll talk a little bit about. And then finally you hit Estefanolga Bluff, which is unimpressive when you compare it to Alum Bluff, but it is the last bluff you really see on the Apalachicola, at least as you head further south. Here's another interesting, this is another, it's a digital elevation model that was created using LiDAR imagery, and you can really tease out some of these interesting, these are all coastal relict strand plains, and you can see dune fields in here and all kinds of neat stuff. So LiDAR imagery is incredibly useful, particularly here in Florida, for making representations of topographic relief. And it's incredibly important for us because it allows us to actually strip off the vegetation and really look at what the underlying topography is. And you can tease out all kinds of really interesting features from looking at LiDAR. So again, starting all the way up north near the dam at Lake Seminole, the first and oldest geologic unit you can see exposed along the Apalachicola River is what we call the Chattahoochee Formation. It is an early Miocene limestone unit, and it was deposited probably sometime around 20 to 22 million years ago. And when the river is low enough, this is what you see. This is looking south. Here's the old railroad trestle over the Apalachicola River just south of Chattahoochee. And what's interesting, I don't know if you can see this real well, but look how clear this water is. This is not typical Apalachicola River water, and it's because there are springs that discharge all along here, and they're discharging groundwater from the upper Floridan aquifer. This is one of the few places along the Apalachicola River where it actually gets some of its base flow from springs. As we head further south, we get to the famous Rock Bluff exposure here at Torreya State Park. This is another limestone unit. It's called the Torreya Formation, and it was deposited also during the early Miocene, but it is not quite as old as the Chattahoochee Formation. It was deposited about 19 million years ago. And again, you know, this is a marine limestone. So in order for this limestone to have been deposited here, obviously sea level would have had to have been higher than it is today, and it certainly was. And something else I'd like to draw your attention to is as the state geologist, I have statutory authority to designate sites as state geologic sites, sites of importance to the geologic community, and Rock Bluff happens to be one of those sites. So if you're interested in learning more about that, I'll tell you how you can do that here at the end of my talk. But I dedicated this as the 6th designated state geologic site on February 21st of last year. As you head further south along the Apalachicola River, you ultimately come to this amazing bluff that we call Alum Bluff. And this is Florida's tallest natural geologic exposure. There's about 125 feet of exposure here when the river level is low enough, and you can see 4 geologic formations exposed at Alum Bluff. And those geologic formations, starting from the oldest down here at the river level, include the Chipola Formation, what we call the Alum Bluff group, an undifferentiated formation within the Alum Bluff group. Then sitting on top of that is the Jackson Bluff Formation. And then finally, all the way up here at the top is what we call the Citronelle Formation. We'll talk a little more about each of those. So the Chipola Formation is also an early Miocene deposit. It's about 18 million years old, so it's very, very close in age to the Torreya Formation. And it turns out the Torreya Formation and the Chipola Formation probably do what geologists call interfinger between the exposure here at Alum Bluff and the exposure up at Rock Bluff. And what's really neat about the Chipola Formation is it's incredibly fossiliferous. And you can see this here. This is a picture at Alum Bluff, and you can see how full it is of all of these marine critters, mostly mollusks. But there's a whole bunch of different things that occur in here. And this unit has been studied intensively by paleontologists for many, many years. It turns out there are probably on the order of 11 to 1,200 different species of mollusks that have been identified in this unit. There are corals in this unit. There are cephalopods that come from this unit, all kinds of neat things. And the reason it's so diverse is this represents the last time that conditions in North Florida were actually truly tropical. So you can envision this as a tropical sea. It was obviously highly biologically productive, and the remains of all these organisms were buried and lithified, but the preservation on these shells is quite spectacular. It's pretty amazing that 18 million year old shells can still have some of the nacre on them. Another interesting feature that we discovered in the last 10 to 15 years, and myself and a couple of colleagues actually described these features. This is a stromatolite. And for those of you that don't know what stromatolites are among some of the oldest living things on the planet. The stromatolite itself is actually a geologic feature, but it was created by the buildup of probably blue-green algae. And the algae existed as mats, probably on a very shallow mud flat. And over time, those mats would grow up, and then they would catch sediment, and then the filaments would grow up again, and that sort of creates this concentric structure you see here. So stromatolites, at least in the Cenozoic, and particularly in Florida, were not known until we documented these here at Alum Bluff. And when water levels are low enough, you can actually see this at Alum Bluff. It's pretty spectacular. Sitting on top of the Chipola Formation is what we call this undifferentiated formation in the Alum Bluff group. And it's also interesting for its fossil content. And what you can see here in these intensely cross-bedded deposits is in between some of these sandy layers, you see these darker layers here. Turns out these are organic rich layers that are actually chock full of fossil plants. And this is one of the most productive fossil plant-bearing units, certainly in Florida, but maybe in the entire southeastern US. And it's famous for producing giant palm fronds. This is called a Sabolites apalachicolensis, but it also produces petrified wood, and a number of paleobotanists have looked at this deposit and identified the flora that existed during the time that this was being deposited. This was being deposited during what we call the Middle Miocene, probably around 12 million years ago, give or take a few million years. And it turns out that conditions were probably more on the temperate side, but somewhat similar to what we see today in the modern floodplain of the Apalachicola River. But interesting that all of these fantastic plant remains would be fossilized. You know, plant fossils are pretty rare in the fossil record. So we're pretty well endowed with fossils here. The next geologic formation that sits on top of that Alum Bluff group undifferentiated unit is called the Jackson Bluff Formation. And notice that the Jackson Bluff Formation was deposited during what we call the Pliocene Epoch. So between the deposition of the Jackson Bluff Formation and the deposition of the formation under it, we're missing millions of years of time. And that's always something important to keep in mind, particularly when you're looking at the geology of an area. You really only have, if the geology is a book, most of the pages are torn out. And so usually all you have are a couple of little pages to tell you something about the geologic history in an area. And that's certainly the case here at Alum Bluff. The Jackson Bluff Formation, as you can see here, this dark material, it's kind of an organic rich clayey sediment, but it is chock full of, again, fossil marine organisms. And it's probably dark because this was probably an estuary, but it also has, quite a good diversity of mollusk species, nowhere near what the Chipola Formation had. It turns out, based on an analysis of the fossils, we know that waters were cooler during the deposition of the Jackson Bluff Formation. And you see here, these are some of the taxa you can find in the Chipola Formation, including this unique and interesting gastropod here that we call Ecphora. It's an indicator species of the Miocene and the Pliocene. And then sitting on top of that, the Jackson Bluff Formation is a formation we call the Citronelle Formation. And the Citronelle Formation is really just a giant accumulation of quartz sand. And you can see a little bit in here, you can see some of the bedding in here, that's called cross bedding. And that tells us a little bit about how this sediment was deposited. But all of this was probably brought down here by rivers and streams, and it accumulated in these fairly thick deposits that cover most of West Florida. So from about the Apalachicola west, where it hasn't been eroded away, you have a nice thick cover of this quartz sand. You can also see some quartz pebbles in here as well. As we continue heading further south and you get to Bristol, there's a nice cut bank and bluff exposed at Bristol. And in that bluff, this is what you'll see. And again, you see the nice bedding structures in here, this cross bedding, probably indicative of a meandering river channel as the river meandered back and forth in its floodplain and changed, ultimately could change the relative current directions, which is why you actually get cross bedding. But this is also the same deposit that we see at Alum Bluff, and down here it's not quite as full of plant fossils, but we do find carbonized logs and other things indicative of the Alum Bluff group undifferentiated. Well, and finally, for those of you that are interested and you want to learn more about the Apalachicola River or about geology at any part of the state, I certainly encourage you to visit our website. And here's the link to our website. If you come down here, you can go to FGS Publications. We've got hundreds and hundreds of publications available and maps and all kinds of geologic data. And hopefully, if you're interested in any aspect of Florida's geology, you ought to be able to find something about it through our website, and I would encourage you to do so. And with that, I thank you all, and I'd be more than happy to take questions.
Thank you so much. We really appreciate your talk. Feel free to come off mute, or you can type your question in the question box. I know it takes a couple minutes to get there, so I'll be watching. I've got a couple in here. Let me pull this out.
I'll leave this part of it up in case somebody wants. But you can also just Google Florida Geological Survey.
If you'd like to ask your question verbally, you'll have to use the raise hand feature, and then we can unmute you from here.
Trying to tell who this is from. For some reason, I can't tell, but they say amazing information. Thanks. 3 questions.
This is from Kelly Hornsby.
Oh, thanks, Kennedy. The man behind the curtain is Kennedy Hansen. Thank you. He has 2 screens. Kelly says 3 questions if there's time, and I think we have plenty of time. Question 1, why is there so much kaolin on the Georgia coastal plain, whereas North Florida doesn't have such basement of kaolin? I get the idea that
kaolin, clay?
Yeah, I think that's what she meant. It says, I get the idea that corals deposited many carbonites, but why aren't there more aluminum silicates? Am I saying that correctly?
Well, so there are kaolin deposits in Florida, and ultimately those deposits come from the weathering of minerals we call feldspars. And it turns out feldspar is nowhere near as hard as quartz. So that's why quartz sand typically makes it much further being transported by rivers and by longshore currents than feldspars do. So up in Georgia, there are big kaolin deposits, but they occur right at what we call the fall line, which is the division between what we call the Piedmont province and then the coastal plain. So the weathering of feldspars is occurring right there. And that's where these, major deposits of kaolinite occur in Georgia. But down here in Florida, we're so far removed that the amount of feldspar that makes it down here and is available to weather just is nowhere near what it is up in that part of Georgia. Does that answer your question?
I don't know, Kelly, did that answer your question? Okay, and we have a
We got
couple
a yes
more.
in the questions box from her. Yeah.
Okay, great. For some reason, I'm not able to see that. Kelly also asked, why is there so much more iron oxides in South Georgia and South Alabama versus North Florida? I get the the oxidation of iron sulfides deposited iron, but where's the iron in North Florida?
Well, we actually do have some iron in North Florida. It typically occurs as a crust or a layer, oftentimes in the subsurface, and it's deposited as a sort of a mineraloid that it's not hematite. It's called limonite, and it's an iron oxide that's got some water locked up in its structure, so that's why we call it a mineraloid. But again, probably the reason is because of our proximity to sources of those irons, of iron. So, we're way down here in Florida. We're far removed from the sources of the rocks that originally would have, broken up and eroded and been the sources of the iron you're talking about. But we do have it here in Florida.
Okay, last question from Kelly is, oh, sorry, my screen keeps shifting. Does the Apalachicola have a deep water cut in the greater Gull? Does that imply the river was longer in the past?
So I'm gonna assume what she meant was Gulf instead of.
Yeah. Oh, again, yes.
So certainly when
Gulf.
when sea level was lower, obviously the emergent portion of the Florida platform, when sea levels were lower, that river flowed through that. So yes, the Appalachia was certainly longer, and it was certainly longer during the last glacial maximum of about 18,000 years ago, when sea levels were 350 plus feet lower than they are today. So then I talked a little bit about that when we talked about the Holocene portion of the river. And we know from vessels that have taken what we call seismic surveys, so they release energy, and that energy goes down into the subsurface and is reflected back, and the reflection times are recorded, and then you can take that back and run it through some computer software, and you can tell something about the subsurface. And usually what that shows is that there are these deep features that are former channels of the Paleo-Apalachicola River that have been filled in because that river channel has changed and migrated over time. So the ultimate answer to your question is yes, the Apalachicola has been longer in the past when sea levels were lower.
Great. And then from Kay, she asked about the dam in Georgia. There is a dam on the state line. There are many dams on the river system.
There are.
And I believe she's talking about maybe the dam at the state line.
Jim Woodruff?
Yes. And then from Gene, we have, where was the controversial, in quotation, exploration well focused, and what was the target formation?
I don't understand the context of that question. What?
There's a lot of interest in exploratory wells that were being drilled, I believe, in Gadsden County.
Oh, you're talking about oil and gas wells.
Yeah, oil and gas wells. Yeah, sorry. Yeah.
Okay.
And they were exploratory wells, and
yes, they were.
I guess she's asking what was the target formation.
Oh, so they were targeting all the way down into strata of Jurassic time. So probably all the way down into what's called the Smackover and the Norphlet sandstone. Those are the geologic units that are typically targeted out in West Florida for the production of oil and gas resources. And so that's what they were probably targeting. But all of those wells that were drilled were dry wells.
Yeah. And then David Adlerstein is our local ACE reporter. He asked, I'm curious about the geological history of the dolostone that will be used as deposited in the bay as culch to grow oysters on. If you have any insights on that.
Yeah, I do. So the geologic history of it is going to be dependent on where that material is brought from. And just to give you some background, dolostone is a carbonate material like limestone. So limestone is comprised of the mineral calcite, as dolostone is comprised of the mineral dolomite. And dolomite is equal parts of calcium and magnesium attached to the carbonate. So there's magnesium in dolostone. And it turns out in Florida, for the most part, dolostone is a function of weathering of limestone, typically chemical weathering. So we don't have dolostone deposits for the most part in Florida that were originally deposited as dolostone. They were deposited as limestones, and over geologic time, chemical processes took place, and magnesium was introduced into the unit, and it sort of changed the chemical properties, and it sort of slowly over time turned into dolostone.
Yeah, I think, and maybe correct me if I'm wrong, but we're worried, we're concerned that about its stability, because the fossilized shell that was put out in the bay during the last few restorations is disintegrating. So I know we're looking for a harder.
So dolostone should be a more consistent substrate. In other words, it shouldn't degrade like the calcium carbonate shells that were being put. And I don't know all the history of what it is that they have been using in the past, but if they were using fossil oyster shells, oysters are themselves made out of calcium carbonate, calcite, so they can degrade over time. But dolomite, the actual mineral dolomite, is harder and more resistant to dissolution than calcite is. So putting dolostone out there as a substrate, that ought to be less resistant, more resistant to erosion over time than what has been put out previously.
Great. We're looking forward to that. And I think it will be mined here in North Florida. David mentioned that. This is Kate Snyder. She asked, what geological feature do you think is most meaningful culturally or historically along the river?
Wow, that's a tough one. Well, I can imagine that Alum Bluff was probably pretty culturally significant, just from a strategic standpoint. It's so tall and sits right there overlooking the river. You can see up and down it. It would have been a fantastic spot, and we know people lived on it for many thousands of years. Some of the geologic units that are exposed a little further north along the Flint River were probably more utilitarian to the native people, because that's where they got the stone that they used to make their tools. So chert is the name of that material, and it occurs naturally in the older geologic formations that occur above where the current dam is today. And too bad we couldn't see what that looks like. It would probably be pretty spectacular. Imagine, if you will, Lake Seminole now sits on top of where the confluence of those four, creeks and rivers came together to form the Apalachicola River. And there, we know there were springs and all kinds of things that are, now completely underwater under Lake Seminole. So
Yeah.
wished I'd had the opportunity to see it before they drowned it.
Yeah, and many other spots if we could see clearly.
Yeah. Kate, does that answer your question?
We've got one more question here from Jim Folsom. Are the exposed soil in the Swanee River Basin younger than those in the Apalachicola Basin?
Exposed soil? Is that what he asked?
Exposed soils, yeah. He's a botanist. If it's the same, Jim Folsom.
It depends on where in the Swanee Basin you're talking about and where in the Apalachicola Basin you're talking about, if that makes sense.
Yeah.
So, you know, the lower parts of the Swanee River, some of those soils could potentially be older, but, you know, that's a good question. I'll have to say, I don't know the answer to that right off the top of my head.
Okay, great. Well, I'm afraid we're out of time. So I want to thank you again for speaking with us. And it was great, a lot of really great information. And we hope all of you will join us for our next Sci-Cafe, which will have Dr. Nancy White. She's a professor, University of South Florida, and she works a lot on the Apalachicola River. I think she also agrees with you that the river mouth has changed over the years. And she's going to talk about some of the archaeological investigations they've conducted around the Apalachicola River Valley for many, many years. And that will be September 21st. From 3 to 4 p.m. So thank you, Harley. Guy, I'm not sure which you'd like to Harley. Bye. But thank you so much. It was a very informative session, and we look forward to seeing everybody in the future.
Fantastic. Well, I enjoyed it, and thanks everybody for attending. And Anita, thank you again for inviting me. I greatly appreciate it. And I'll also put a plug in for Nancy. I would encourage everybody to attend that. Some of the information that I provided you today is actually based on some of Nancy's work, you know, looking at the ages of some of the features at the mouth of the Apalachicola River. The only way we can date them is by the archaeological material that occurs. So she played a big role in that.
That's great. Well, thank you. And the recording, we'll send out an email with the recording link. Give us a few days. Alicia is on vacation, so we'll try to get it up next week, but it's on our website. So thank you once again, and we'll see everybody next month.